Welcome to Graphing Rational Functions. Guys, we have reached pretty much the end of this module on rational functions, and so I want to put together everything we've learned the entire module. So at the end of this video, you should be able to have everything you need to graph a rational function. The roots, the y-intercept, the vertical asymptotes, the domain, the end behavior, the horizontal asymptote, and we're going to practice graphing one rational function here. So we're going to go step by step, and we are going to break down each piece of how to graph a rational function. Now, I want to start by remembering what a rational function looks like. This is our parent rational function right here. I like to say it kind of looks like two boomerangs. What we see here are asymptotes on the x and y axis, and the graph follows those asymptotes. It is drawn to those asymptotes. It is almost magnetically attracted to those asymptotes, meaning it's going to get closer and closer to that horizontal asymptote of 0 but never touch it, and it's going to get closer and closer to that vertical asymptote of 0 but never touch it. And that's a huge defining feature of the graph. So as we find all of these different parts of the rational function, the roots, the y-intercept, the vertical and horizontal asymptotes, remember that when it comes down to graphing, those asymptotes are the defining feature. So let's dive right in. The first thing I want to talk about are roots. When we are talking about roots, we are looking strictly at the numerator of the function. So let's break this function in half and let's just focus on the numerator. And this is where we're going to find our roots. We don't really care what the rest of the function is. For the time being, roots are mainly focused on the numerator. And it's important to say that when we say roots, we also can be saying zeros. We also can be saying x-intercepts. These are all interchangeable. Solutions is another word you might hear. So how do we find the roots? We're looking just at this numerator, and we are setting the numerator equal to 0. This usually involves some factoring, but mainly we are going to solve for x. That's pretty straightforward. That's the same process we've done for every single function we've seen. We are setting it equal to 0 and solving for x. The only difference with rational functions is that we are mainly looking at the numerator. We don't have to consider the denominator, because if we think about a fraction, if the numerator of a fraction is 0, it does not matter what's in the denominator, any number in the denominator, and we're still going to have a result of 0. So what about the y-intercept? The y-intercept, we can't just look at the numerator, we have to look at the whole function. So what we're going to do with our y-intercept is what we've done with every other function we've ever seen. We're going to plug in x everywhere, both the numerator and the denominator. So we're going to plug in 0 specifically. And then we're just going to evaluate that function, meaning simplify it down to get that result. Now, I think it's important to note that our y-intercept will be in the form of 0, comma, a number, and our x-intercept will always be in the form of a number, comma, 0. And writing those as ordered pairs is going to be really helpful when we go to graph. So those are two features we've seen in every graph we've pretty much done since Math 1 and maybe even earlier. Let's talk about the newer features, namely our vertical asymptotes. Our vertical asymptotes are just like asking what makes the fraction undefined. What makes our fraction undefined? And there's really only one thing that causes a fraction to be undefined, and that's dividing by 0. So our vertical asymptotes come from the denominator because we're specifically looking for places where we're dividing by 0. So just like we did with the roots, we are going to set the denominator equal to 0. This is usually going to involve some factoring, but ultimately we are solving for x. Now we're finding equations of lines. So our result is going to look like x equals a number. because that is the equation of a vertical line. And this is directly connected to our domain. In fact, this is why our domain is not all real numbers. Our domain usually is negative infinity to positive infinity. That's a traditional domain for most of the functions we've seen, but it's not going to be this because we have these vertical asymptotes breaking it up. So for example, if I were to just show the x-axis of my graph, we'll start over here at negative infinity. We'll have values all the way up to our first vertical asymptote, and that value will be undefined. That value will not be allowed to be plugged into our function, or it's excluded from our domain. Then we have all the values again until our next vertical asymptote, which is again an undefined value or value we can't plug in. And then our numbers keep going until positive infinity. So when I think of the domain, I think of placing all of our vertical asymptotes on a number line and just excluding those values. So exclude all vertical asymptotes, but otherwise we are just going negative infinity to positive infinity. So what about the horizontal asymptotes? For the vertical asymptotes, we're able to just focus on the denominator, but for the horizontal asymptotes, we can't. For the horizontal asymptotes, we have to look at the function as a whole, because what we're asking is what is the heart of this function, or what is the true nature of this function? What does it look like when we zoom out and just see it as a whole function? And that's why it is tied to end behavior. So our end behavior looks at the entire function as a whole, both the numerator and denominator, and it asks the question, is this a proper or improper fraction? Because we can predict what's going to happen in fractions if we know whether it's proper or improper. So let's start with the case of proper. Now, in a proper fraction, the denominator is always larger. The denominator is always larger. And what happens when the denominator keeps increasing at a higher rate? Well, what happens to a fraction when that denominator gets so large? 1 over 10 is small, but 1 over 100 is even smaller. 1 over 1,000 is even smaller. 1 over 1 million is even smaller than that. In fact, if I told you you got 1/1,000,000th of this pizza that I'm cutting up, it's virtually zero. You're virtually getting no pizza. So when we think about proper functions, as we go to the ends of the graph, as we plug in these giant numbers, they become these impossibly small fractions. And so that's why we say as x goes to the ends of the graph, plus and minus infinity, our y value essentially goes to 0. Now, is it ever going to equal 0? No, because those fractions will never be 0, but it'll become impossibly close to 0. All proper rational functions will do this, all of them. So what about improper? So for improper, we're forced to think of two different scenarios. What if the degrees are equal? What if the degrees are equal? Because at the heart of this, we're really just dividing. We're just dividing. If my degrees are equal, well, then that x divided by x perfectly matches each other as we go towards infinity. That x squared over x squared perfectly matches each other as we go to infinity. That x cubed over x cubed perfectly match each other as we go to infinity. So what is left over? What is left over if the numerator and denominator are always kind of right in pace with each other? Well, as x goes to positive and negative infinity, our y just goes to the leading coefficient. That leading coefficient is all that's left behind if we're dividing the numerator and denominator. Well, keep that idea of division. What happens if it's improper? With a greater degree in the numerator, where the numerator is greater than the denominator. If we keep that idea of division, well, x squared over x is going to result in just x. X cubed over x is just x squared. X squared over just constant is going to be just x squared. If we keep that idea of division, we're able to divide and find that our end behavior could look linear, like x. It could look quadratic, x squared. It could even look cubic, x cubed, or quartic, x to the fourth. So this does not have this perfectly predictable horizontal asymptote. It actually has lots of different combinations of positive or negative infinity, and that's going to be dictated by the division. Divide and get that result each time. So I'm going to put a little asterisk next to these. Divide, and we will find the exact end behavior, the exact horizontal asymptote. So how does end behavior tie to horizontal asymptotes? They are the same thing, just phrased differently. Our horizontal asymptote for proper, well, we said they go to 0, so it's just y equals 0. Our improper with equal degrees, we said it goes to the leading coefficient, so y is just going to equal the number of that leading coefficient. And we said that there's no flat line. There's no just solid number or some constant number for those improper where the numerator is greater. So there's no horizontal asymptote. So these go hand in hand. They're just written different ways. So this is everything we need. We need the roots, which we know come from the numerator. We need the vertical asymptotes in the domain, which come from the denominator. We need that y-intercept, which is just plugging 0 into the function. And we need that horizontal asymptote, which is evaluating that function and thinking, if I were to treat this as division, not just as a fraction, but as division, what would my quotient or result be? Let's put this all into practice with an example. So here we have a rational function, and we're going to break down each piece of it and then try to sketch it. So let's start with our x-intercept. Let's start with our x-intercept. We know our x-intercept comes from the numerator. So we're going to take that and set it equal to 0. X plus 1 equals 0. Subtract 1 from both sides. X equals negative 1. So our x-intercept is negative 1, 0. And let's plot that. Don't overthink this one. It is as simple as that, just taking the numerator, setting it equal to 0. Now what about the y-intercept? Well, the y-intercept is plugging in 0 everywhere. F of 0, 0 plus 1, over 0 minus 2, 0 plus 2, is just 1 over negative 2 times 2, negative 4. So our y-intercept is 0, comma, negative 1/4. And again, let's plot that. Don't overthink it, plot it. So moving on to our vertical asymptotes, we're asking the question, where is my function undefined? Where is my function undefined? Well, that comes from our denominator. We cannot divide by 0. So let's set that equal to 0. We have two factors, so each factor individually will be set equal to 0. So x minus 2 is set equal to 0, and x plus 2 is set equal to 0. That gives us one asymptote at x equals 2. And one asymptote at x equals negative 2. Remember, we write those separately because they are two separate lines. They are two distinct lines on the graph, so we want to write them separately, 2 and negative 2. Okay, so we took care of our x-intercept, that's plotted there in red. We took care of our y-intercept, that is plotted there in yellow. We took care of our vertical asymptotes, which will be connected to our domain. So if we wanted to add our domain there right now, we could. Looking at our graph, we could say our domain starts over here at negative infinity, breaks right here at negative 2, keeps going between negative 2 and breaks again here at positive 2, keeps going after 2 all the way over to infinity. So there is our domain. What this is telling us is that we're going to have points everywhere on the graph except for negative 2 and 2. So it's going to look like we have multiple graphs, but we really are just filling the entire graph except for those vertical asymptotes. So last things last, let's talk horizontal asymptotes. Our horizontal asymptote is imagining that we're dividing this function. So what I'm going to do is I am going to rewrite this looking at the degree of the numerator and the degree of the denominator. So when I rewrite this and I'm looking at the degree of the numerator, degree of the denominator, I have this x over x squared. Here I have this situation where as I plug in larger and larger and larger and larger and larger numbers, my numerator is going to be always, always, always smaller than the denominator, and not just a little bit smaller. By the time we get to infinity, it's going to be a lot smaller, a lot smaller. So we're imagining this fraction where our denominator is a very small number. Our numerator is a very small number and our denominator is a huge number. This is exactly the scenario that approaches 0. We end up having a fraction so small that it just keeps getting closer and closer and closer and closer to 0. So we would say as x approaches the ends of the graph, positive and negative infinity, our function f of x, its y values approach 0. So essentially at the very ends of the graph, we're going to see our function taper off, our y values taper off to 0. And that means our horizontal asymptote is just y equals 0. Now we're going to take the next little step and we're going to sketch this. We're going to graph it. But you don't have to do that just yet. If you want a little preview of that, how would we actually graph this? Well, we would have to connect the dots. We know that these two have to connect. Our x-intercept and our y-intercept have to connect. And it's not going to go back up over the x-axis again. If it was going to do that, we would have another intercept, but we don't. So this is just going to have to keep going down. And because, like we said earlier, the asymptote's going to dictate the shape of this graph, I know it's going to be drawn to that asymptote. It's going to be almost magnetically pulled towards that asymptote and followed down to negative infinity down there. Well, in the same way, the other side is going to be magnetically pulled to that asymptote and drawn upward to positive infinity. And one of the features we're going to see is that our asymptotes always flip. So if I have positive infinity on this side of the asymptote, I'm going to have negative infinity on this side of the asymptote. So my graph is going to start down here and stay underneath our horizontal asymptote of y equals 0. So again, we have negative infinity on this side. We're going to flip upward to infinity on this side, meaning our graph starts up here and stays above that horizontal asymptote of y equals 0. So there you go. That's the graph. Will we always see this kind of inversion or flip from negative to positive infinity at asymptotes? No, there will be an exception to this whenever we have multiplicity. Look for that in task 2.6. Okay, so hopefully this was a good example of how to find x-intercepts, how to find y-intercepts, vertical asymptotes, and end behavior. We're putting this all together and graphing it from here on out.